Dante 2, an 8-legged walking machine, is shown here during field trials with its action sped up. Named for a 14th century Italian poet, this 20th century robot has been designed to withstand and report on its journey to the floor of a volcano. NASA sponsored a team from Carnegie Mellon University to build Dante, a robot designed to withstand Earth's harshest conditions. Its goal, prove out technology to explore distant planets. Remotely controlled from 80 miles away, the robot was able to investigate the inner depths of an active volcano at Mount Spur, Alaska. Spur's caldera is an open pit of steaming vents, surrounded by sheer walls of fractured rock.
There's everything from pebbles to car-sized boulders rolling down all day long. We tried to pick a descent course that would protect, insulate the machine from most of the rockfall.
John Bears heads the CMUT. With help from the Alaska National Guard, Dante was airlifted safely to the crater rim. Mount Spur's crater erupted in 1992. One of the robot's functions was to measure levels of volcanic gases. This information gives Mike Dukas of the Alaska Volcano Observatory an idea of how active the crater might be.
It has gas sensors on board. It has a sulfur sensor, a carbon dioxide sensors. And so that's going to give us a real close-in view and sampling of what the fumaroles are made up of.
In the past few years, 11 scientists have perished while working near active volcanoes. This danger makes robots an obvious alternative.
If you are in the wrong place at the wrong time, the person standing next to you will die and you won't. And so it's a matter of, you have to ask that question, why are you going into that zone? Is it necessary for you to go into that zone? Can you do that same measurement from a safer position?
Because of the ever-present danger of an explosion, scientists monitored seismic activity and kept constant radio contact with the team on the crater rim. In 1993, the first Dante robot attempted to explore Mount Erebus in Antarctica. When its fiber optic communications cable snapped, the mission was cut short. But according to CMU's John Bears, the mission taught them some valuable lessons.
We looked at the experience from Dante 1, which taught us an awful lot about what would work, what wouldn't work, what was appropriate for the environment, what was appropriate for the terrain, what was appropriate to take on in a year. And then we came here and looked at the volcano.
To improve its systems, major design changes had to be made quickly to keep the project on schedule. It was done with the help of experts in laser technology, telecommunications, computer software, and mechanical engineering. After power was supplied to the robot from a generator and all communications links were set, Dante was ready.
Henning, I think we're ready to stand up and try stroking and turning.
I think you're correct.
The 8-legged craft began its assault on the crater.
When you get a second, Henning, give us your tether payout.
We're at 90 meters.
Special rubber snowshoes helped it traverse the first snow fields. Ultimately, Dante spent 3½ days traversing the nearly 700 feet down to the crater floor, an area covered with boulders. Information from onboard video cameras and sensors was relayed via satellite to scientists in Anchorage. From their remote location, controllers used a computer-generated image created by a laser scanner to track its movement.
In addition, they had a computer display that was, in effect, the robot's dashboard that gave them information and feedback from all the onboard sensor systems, told them when the legs were in contact with the ground, what angle the legs were positioned at, what attitude the body had with respect to gravity in the ground, that sort of information.
David Lavery is manager of NASA's telerobotics program. Dante also incorporates virtual reality technology developed at NASA Ames Research Center. The system gives the user a feeling of being there.
What it is a pair of cameras that are set at the human ocular distance, or roughly that, and then those cameras, frames from those images, are sequenced back at the operator station using a special monitor and a special glasses so that the human is able to perceive some depth.
This same technology has been tested in a number of applications by NASA. Martian rover prototypes and underwater explorers have been operated remotely using 3D visual displays and specially censored gloves. Artificial intelligence allowed Dante to navigate on its own.
A lot of what we learned had to do with how much autonomy can be used on board a robot, given our current level of technology, to navigate through the extremely rugged terrains that we saw inside the crater. We had a capability for at least half of the descent to basically turn on all of the onboard intelligence on the robot and let it do its own thing.
Although the extremely treacherous terrain impeded Dante's climb from the crater, all science and technology objectives were completed, indicating that the crater will probably remain inactive. It proved that exploring dangerous terrain was possible using unaided robotic technology. CMU graduate student Demetrius Apostolopoulos.
It's becoming almost like a life goal. Every single person that got involved in both projects has made their decisions to try to make something happen and make it known to the outside world.
Having accomplished one short-term goal with the successful descent into Mount Spur, the robot team hopes to apply the lessons learned to NASA's long-term plans for the future.
Our hope is that a lot of that will find its way into future planetary missions. That's obviously where NASA's interest lies, is we want to take this and move it out to the surface of other heavenly bodies, the Moon, Mars, and other planets.
Carnegie Mellon University robot called Dante has been rescued from a crater in Alaska. What does it mean for robots in our future? Scott Bemke and Henning Pengels of the CMU Robotics Institute are the guests of editor John Craig and science editor Byron Spice.
We're talking about technology again in this segment, and now we're talking about something that's just attracted wide attention. That's Dante. Tell us about that.
Yeah, well, Dante is an 8-legged mobile robot, as opposed to, I think we've become quite accustomed to robots assembling cars and doing this sort of thing, but those are robots that are stationary. They sit in a plant, they're in an environment that everything's controlled. Carnegie Mellon has been working for some time on field robotics, mobile robots that are able to negotiate highways, fields, and in this case, walk over boulders, around boulders, across crevices. Dante was designed to explore a volcano, an active volcano about 80 miles west of Anchorage, Alaska, called Mount Spur. Late last month, Dante was helicoptered to the rim of Mount Spur. There it was assembled, well, it was already assembled, but they anchored a tether at the rim. They set up some telecommunications equipment, generator, and then basically left it. And from that point on, the robot walked either on its own or under the control of the staff about 80 miles away in a trailer in Anchorage, walked down about 700 feet into the volcano, walked around inside, sampled gases, then started walking back up. On the way back up, it ran into some trouble, flipped on its side, and it was only about a week ago that they were able to retrieve the robot by going down, putting a sling around it, and helicoptering it out.
So we have two of the people who worked on Dante. Scott, were you there?
I was there for the entire mission.
And what did we learn about this? What did you think?
It's a lot of experience in building robots that are designed to withstand that kind of an environment. A volcano is an extremely harsh environment. There's acids, there's very fine ash, there's lots of water and steam, and designing a system to run in that kind of an environment is a significant challenge, and it prepares a lot of us to go on to further missions, possibly even in space.
Did it work?
Absolutely. We achieved our mission goals. We got down there, we got the science that we were looking for. The robot basically was untouched the entire time. One small trip to the rim to fix something that was on the rim of the volcano, and the robot went down and back up, mostly back up flawlessly.
Now, the fact that it didn't get all the way up to the top, obviously that's attracted a lot of attention, but I mean, do you see that as a major issue, or is that...
In a sense, I'd say it's not that big of a deal, because we learned what we came to learn. It would have been nice to have a robot intact afterwards, but the end result of our work is not so much the piece of hardware, but what we've learned from the experiment. And after all, you know, this is research, and what we did was an experiment.
So the things that you learned was, one, that you could design a machine which could withstand rather severe climatic and other issues. Is that right?
Right. Even the terrain we were on was very unstable. It's difficult to navigate around the boulders and through the crevices. And there's also a significant challenge in teaching the robot how to actually work in those conditions on its own. And I think there were a lot of significant software advances in that area.
Well, that's software. That's your department.
Primarily, yes.
And what's different about this robot?
Well, for us, it was the first time we really developed a capability to teleoperate a machine over that kind of a telecommunications link. We had a satellite link with about a half a second delay in the data transmission, which created a bit of a challenge, and we certainly learned a lot about what it takes to deal with that, and how to effectively maneuver through terrain that you've never seen except through the eyes of the robot as it goes through it. So that's, for us, that was something new, and I think also a significant a part of what the NASA research thrust is after.
So where do you go from here? What sort of things does this make possible that you might have not have thought of before?
Well, we got a lot of good ideas about additional ways to perceive the terrain for an operator, certainly. We got an idea of what it takes to, how much concentration it takes to walk the machine through very rugged terrain. And we got ideas on how to develop software to do a lot of that work for us, more computer-assisted teleoperation, if you will.
Now, Scott, you said you can get the machine mechanically. The machine can do this. Software, who's running this machine? Somebody looking at a screen, or is the machine actually running itself? That's one of the parts that's a little hard for me to determine. How much of this machine, how intelligent is this machine?
Well, as often the answer is it depends. Ultimately, it's a person sitting there at a computer screen with a couple of video monitors, getting the pictures back from the robot, and on the computer screen a graphical interface with a mouse and a keyboard, where you have a display of what the robot senses, and you can tell the robot what to do. Now, what you tell the robot to do depends on what you decide to let the robot do, if you will. We have
what I was thinking about, let's suppose now we're going back and the Eagle Dante has landed rather than the Eagle.
Mm-hmm.
So nobody hops out of Dante. Dante's now on the moon, and he takes out his golf club and hits a golf ball, and he plants an American flag and all the rest of these things. I mean, but really, he is doing this because somebody's looking at a screen telling him to do this thing, or is he pre-programmed to react to certain things? I mean, how much of this is anticipated, or how much of this improvisation given certain variables, and how much of it actually just has to be somebody sitting there like operating other pieces of machinery?
Well, the further away from Earth you get, the more the robot will have to do on its own, because I spoke about a half a second delay. Somewhere such as on Mars, you'd get 10 minutes, and every image you see 10 minutes old, and it'd be very difficult to tell the robot every specific thing to do. So I think you're mentioning the robot landing. First, it would probably just report back to the Earth Control Station, okay, I'm here, I'm ready, I'm checked out. Now tell me what to do. And then the operators from Earth would tell it maybe something like, go explore that valley over there, or make a round trip of 10 miles and come back and sample terrain or gases or whatever is of interest on that site.
The idea is you're not telling Dante, okay, move your left foot here and your right foot there. You're telling him, go from this point to that point. Mm-hmm. You figure out how to walk there. You walk around these obstacles that you come to, for the most part. I mean, there may be some points where you say, give him some advice, mm-hmm. but for the most part, you want to just be able to tell him to do a task as opposed to, okay, move this arm or that.
That's right. And we found that we had to do a lot more of that during this mission than is really feasible in the long term for bigger missions.
Now, leaving the software for a minute in that aspect of it, now, are there things that you're doing with these machines that are mechanically unique?
Well, we've made a variation of a frame walker in which we're walking on the 4 legs at a time, and working to design these machines to withstand these environments, it is a bit of a challenge. There aren't very many of them out there that would survive that kind of a environment.
You're talking mainly heat?
Actually, heat wasn't really as big an issue as you might think on Mount Spur. The average temperature up there during the day in the sun was about 65. You'll see in any of the video.
So what are we worried about? Cold, dust?
Cold was actually, and dust and rain and ice were actually the more prevalent problems, even the mud. People walking around on the rim could slip and slide around in the mud pretty easily. The snow was there, you were always breaking through the ice. It was a very tough place to be. The cold was actually more of a concern, and particularly in looking forward to Mount Erebus again, where it's typically 40 below, you have to keep yourself warm. That's actually an analog to what would happen on the planets.
Do you anticipate going to Mount Erebus or to another volcano?
The hope's there.
Mm-hmm. What's the nature of the robot universe? I mean, who else is doing the sort of work that we're talking about?
I think, well, there's MIT, there's JPL, there's a lot of the NASA facilities, there's...
outside this country or other people? Who else?
Absolutely, yes.
And does everybody cooperate with everybody else? So or are there proprietary matters involved here?
We've been pretty open with our technologies.
I think in the academic research circles, it's pretty open. We have a lot of contact with Japanese researchers and European researchers. When you talk to companies, they're going to be a little more secretive about what they've developed. But
nobody has, it's not like anybody has figured out the perfect way of doing all of these things. There's obviously a lot of debate as to what's the right size, how many legs, wheels, that sort of thing.
Oh, sure.
And that's still going on?
Yeah.
And you guys, so you figure this is going to, now as a result of this, you've got a heck of a lot of attention. Do you see that this is taking on a new energy as a result of this?
I think we certainly demonstrated that a walking robot has an application, has potential. I think a wheeled machine in that environment would have been just a loser.
Okay,
wouldn't have worked.
Well, congratulations to you. Thank you very much, both of you. Byron, thank you.